Welcome to another exciting episode of Voyager, where we delve into the mysteries of the universe. Today, we embark on a journey to explore some of the most fascinating and enigmatic entities in space, black holes. These cosmic giants, with their immense gravitational pulls, are capable of consuming everything in their path, including light itself. Recent advancements, particularly those made by the James Webb Space Telescope, JWST, have led to some groundbreaking discoveries that challenge our fundamental understanding of the universe. Join us as we unravel the secrets of these dark behemoths, exploring how the JWST has detected a colossal dormant black hole near our solar system and what this revelation means for our comprehension of galaxy formation and cosmic threats. Black holes are among the most intriguing phenomena in the cosmos. They form from the remnants of massive stars that have ended their life cycles in dramatic supernova explosions. Once a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This collapse results in the formation of a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. These cosmic giants possess an event horizon, the boundary beyond which no information or matter can escape their gravitational pull. The event horizon is essentially the point of no return. Anything that ventures past this boundary is pulled inexorably toward the singularity, a point of infinite density at the center of the black hole. Black holes are categorized into several types based on their mass. Stellar black holes, which are formed from the remnants of massive stars, can range from a few to several tens of times the mass of our Sun. Supermassive black holes, on the other hand, can have masses ranging from millions to billions of times that of the Sun and are typically found at the centers of galaxies. Intermediate mass black holes and primordial black holes are other types, though they are less understood. The idea of black holes has been around since the early 20th century, thanks to Albert Einstein's theory of general relativity. According to Einstein's theory, massive objects like stars and black holes warp the fabric of spacetime, creating gravitational fields. This warping effect leads to the phenomenon we observe as gravity. Despite the theoretical foundation, detecting black holes proved to be a monumental challenge. Unlike stars, black holes do not emit their own light. Instead, their presence is inferred by observing their interactions with nearby matter. One of the first black holes ever detected was Cygnus X1, discovered in 1964. Located about 7,200 light-years from Earth, Cygnus X1 is part of a binary star system featuring a blue supergiant star and a second, unseen object that emits strong X-rays. For decades, the scientific community debated whether Cygnus X1 was indeed a black hole. It wasn't until the early 1990s, after extensive observations and theoretical work, that consensus was reached. Stephen Hawking and Kip Thorne, two of the leading figures in black hole research, had significant debates on the subject. Hawking, known for his work on black hole thermodynamics, was convinced of their existence, while Thorne's research also supported this view. Their debate and eventual agreement highlighted the complexities involved in confirming black hole existence. The James Webb Space Telescope, with its advanced observational capabilities, has recently made some groundbreaking discoveries about black holes. One of the most striking findings is the detection of a massive dormant black hole, known as Gaia BH3, located less than 2,000 light-years from Earth. Gaia BH3 was discovered by accident during the analysis of data from the European Space Agency's Gaia mission, which aims to create a detailed three-dimensional map of our galaxy. The discovery was confirmed using the Very Large Telescope, the LT, of the European Southern Observatory in China. Gaia BH3, situated in the constellation Aquila, has a mass approximately 33 times that of the Sun, making it the largest stellar black hole discovered in our galaxy. The discovery of Gaia BH3 challenges existing theories about black hole formation and stellar evolution. Stellar black holes are typically formed from stars with masses several times greater than the Sun. However, Gaia BH3's mass suggests that the star from which it formed did not lose as much mass as expected during its lifetime. This anomaly raises questions about the processes governing black hole formation. The JWST has also made significant strides in understanding supermassive black holes. One remarkable discovery is an extremely red supermassive black hole located approximately 12.9 billion light-years from Earth. This black hole, with a mass of about 40 million times that of the Sun, was observed in the early universe, only 700 million years after the Big Bang. The redshifted appearance of this black hole indicates that it is surrounded by a thick veil of gas and dust. This discovery provides new insights into the early universe and the formation of supermassive black holes. The JWST's observations revealed that the black hole is actively consuming surrounding matter, producing intense radiation and relativistic jets. These jets, propelled at speeds close to the speed of light, are visible as bright emissions in various wavelengths. The discovery of this supermassive black hole challenges our understanding of how such massive objects could form so early in the universe's history. It raises questions about the mechanisms driving their growth and the impact they have on their host galaxies. The JWST also employed gravitational lensing to enhance its observations. Gravitational lensing occurs when a massive object, such as a black hole or a galaxy cluster, bends the light from more distant objects. This bending effect magnifies and distorts the appearance of these background objects. By observing the galaxy cluster at 2744, the JWST was able to magnify the light from distant galaxies that would otherwise be invisible. This technique revealed a quasar-like object with a redshifted appearance, providing valuable data about the early universe. Gravitational lensing allowed scientists to observe the intricate details of these distant cosmic structures and gain insights into their formation and evolution. Recent research has also linked microquasars to the origin of high-energy cosmic rays. Microquasars are smaller versions of quasars, where a black hole devours material from a companion star, producing relativistic jets. One such microquasar, SS-433, has been studied extensively for its high-energy gamma rays. The High-Energy Stereoscopic System, HES, detected exceptionally high-energy gamma rays emanating from the jets of SS-433. These observations suggest that microquasars play a significant role in accelerating particles to extreme energies. The gamma rays detected from SS-433 indicate that the jets are capable of propelling particles to speeds that produce high-energy cosmic rays observed on Earth. The study of SS-433 has provided valuable insights into the mechanisms behind cosmic ray acceleration and the role of microquasars in this process. This discovery highlights the importance of understanding these cosmic particle accelerators in explaining the origins of high-energy cosmic rays. The discoveries made by the James Webb Space Telescope continue to revolutionize our understanding of black holes, the early universe, and cosmic phenomena. From detecting colossal dormant black holes near our solar system to uncovering the mysteries of early supermassive black holes and cosmic rays, these findings offer new perspectives on the complex workings of the universe. As scientists continue to explore the cosmos, the JWST will remain at the forefront of astronomical research, shedding light on the most profound questions about the universe's origins and evolution. Thank you for joining us on this cosmic journey. If you enjoyed this exploration of black holes and the groundbreaking work of the JWST, be sure to click the video on your screen for more mind-blowing content about space and the universe. Until next time, keep your curiosity alive and continue to explore the wonders of the cosmos.